Okay, hello. So last time, in the last video, kind of what we ended with was having a description of these building blocks that we're going to use for these general solutions, right? Where these building blocks were composed of the product of kind of a spatial piece, right, phi of x, and a time piece, g of t, where phi takes this form, it's sine of root lambda times x times some constant, and g takes the form of an exponential e to the minus k. So where k comes from the p to e, it's kind of capital K0 over C rho, but it's just some constant. But the piece is e to the minus k lambda t, where lambda is a positive constant depending on n, and lambda is n pi over L quantity squared. Okay, and so we could explicitly write those things in, but the point is kind of the building blocks that we're using are parameterized by an integer n. Okay, and so in practice we have infinitely many of these building blocks, infinitely many of these pieces that we can use in constructing our general solution. And so now the question is, how do we combine these building blocks to get general solution? And so that's where we're going to kind of make use of the fact that we're working with linear operators, use a superposition principle, as well as incorporate these initial conditions. Okay. Right. So again, the PDE that we're interested in is the heat equation, okay, on a rod for positive time. Boundary conditions, we're saying the temperature has to be 0 at the endpoints for all time. And then our initial condition is just going to be some initial profile, some initial temperature profile. Okay. And so from above, we saw that, well, solutions to at least the PDE and the boundary condition, those are built from these functions, which we might call u sub n, right? Because kind of this piece right here is lambda, and lambda depends on n. But we have a bunch of these building blocks to work with, and these building blocks take the form sine of n pi over Lx times e to the minus k n pi over L quantity squared times t. Okay. And so kind of how we got these were just determined by the boundary conditions. Okay. And so then the question is, well, how can we determine, right, kind of what building blocks to use and what these constants are in front? And so the answer in this case is, right, generally, we're not just going to use one of these building blocks. We're going to have to use multiple of them. But kind of which of these building blocks and what these constants should be, those are going to be determined by the initial condition, right? The initial temperature profile. Okay. And so as a kind of a specific example of trying to match or trying to actually solve one of these equations, right? So here's a PDE, here's the boundary conditions. These tell us that the solutions are going to take the special form of right, sine times exponential. And so now we're given an explicit initial condition. We're saying, right, we want to solve this problem, and we want the initial temperature profile to be this. So as we saw before, right, so if we plug in kind of the form of the solution, except now we're evaluating at time 0 because we have an initial condition. We're going to have some constant times sine of whatever times e to the whatever. Plug in t is equal to 0. That's going to be 0. So then this whole thing is going to be 1. Okay. But this profile right here, right, kind of we're told what this initial condition is, so we're told what this function should be at time 0. Okay? And so what we're trying to do here is, maybe just match kind of one of these building blocks to the initial condition, especially because the initial condition takes a special form. But so if we plug in, right, what the temperature profile at time 0 is, these are going to be equal. Okay? This is 1, and so here, so technically we have a times 1 right there. But otherwise, this is a condition that we end up with, right? 4 times sine of 3 pi x over L. This whole function needs to be equal to some undetermined constant times sine of n pi over L times x. And this needs to be true for all x. Okay. So the question is, right, what should we choose to be C? What should we choose to be N? In this case, kind of your gut reaction, initial guess, however you want to say it, would be, well, let's just match the pieces. We have a sine of 3 pi x over L, sine of n pi x over L. So let's set n equal to 3 so that this is going to match this. Then otherwise, we have this constant out here. So let's set C equal to 4. And so if we make those choices, then we have our solution, right? As we see that, and so maybe I can write it here. Right, so u of x comma t is going to be equal to 4 sine of 3 pi over Lx times e to the minus k 3 pi over L squared t. Okay, so this is going to be our solution because u satisfies this PDE in these boundary conditions. And if we plug in t is equal to 0, we get exactly this. Okay, so that's our solution. Great. We have a systematic way to solve some of these PDEs for very specific flavor of initial condition. Okay. So as another example, right, same PDE, same boundary condition. Together, these are going to tell us that, right, the solution that we care about is going to take this product. It's going to look like a product of two functions where one is just in space, one is just in time. But now we have this initial condition where we're adding two sine functions, right? So this piece right here is what we got before. This piece right here is new. And so we're saying at time 0, our solution should look like this. Okay. And so how are we going to go about this? Well, let's make use of the fact that we have a homogeneous linear equation, so that if we take two solutions to this equation, add them together. So let me say, if we take two solutions to this equation with these boundary conditions, add them together, we're going to get another solution to this whole problem. Okay. And so then our goal will be to say, great, we can add solutions to all of this to get another solution. Let's choose the solutions in a way so that the initial condition is this. Okay. So in this case, if we take this solution, which we had from the last example, and if we add it to this solution, right, 7 sine of 8 pi x over L times e to the minus k, 8 pi over L quantity squared times t. Okay. So notice that this piece right here solves solves this problem, right? Because it takes that product solution, that product format. And then it also solves kind of this initial condition if we ignore this piece right here. Okay, so that's how we got that solution. That's why we chose 7 and 8 pi. Okay. Yeah, so we have these two kind of solutions that solve the PDE. and individually solve a piece of the initial condition. And so if we add them together to kind of define this new function u is equal to, right, this piece plus this piece. Well, what we get is that, so this, the sum of these product solutions still solves this PDE because of linearity in here. Okay. And then it also solves this initial condition, right? Because if you plug in t is equal to 0, say up here, plug in t is 0 in both of these, we're going to get that this goes to 1 and then this goes to 1, right? And so we're left with 4 sine of whatever plus 7 sine of whatever. And that's exactly this initial condition. Okay. And so we checked it by just, plugging everything in. Okay, so then the takeaway is, so if we have an initial condition that looks like one of these sine functions, which might just be one of them or a sum of 2 of them, or more generally, just add however many of them together with some coefficients b sub I. Okay. So equivalently, we could just write this as a sum. So if this would help get you a little comfortable with the setup. So in here, I've written this as an infinite sum. You could say, well, in practice, maybe we're just working with finitely many pieces. And so what that would look like is, instead of summing over infinitely many terms, we just say, well, we have m of these to worry about. Okay. Another way to think of this might be for the finite is we still have this infinite sum, but then with maybe most of the b sub I equal to 0. Okay. So if all of these coefficients are 0 after some point and you just add them together, right, we can still use this way of writing things, but in practice, it'll be a finite sum. Okay. Point is, what we're looking at are initial conditions that take the form kind of b1 times sine of something plus b2 times sine of something different, etc. Okay. So if we have an initial condition of this form, right, well, then we can go back up here and just add these pieces together. Say, add pieces like this together and get a solution. Okay. So now the question is, right, kind of when is this valid, right? For which initial conditions can we write them in this way? So that's what we're going to get at. But so following the notes, if we have, right, an initial condition of this form, the question is, well, what will the general solution be? Essentially the same thing, just with that exponential piece. Okay, and this is exactly what we saw kind of above, because each of these terms individually satisfy the PDE and boundary conditions. If we want them to solve the initial condition, this term is going to go to 1, and then we just need to match up this piece with our initial condition. Okay. So this is true in general for homogeneous problems, right? Kind of solve for these building blocks, add them together to get your general solution. If you have a non-homogeneous problem, or if you have a non-linear differential operator or formulation, then this approach, as stated, doesn't quite apply. But for the PDEs that we're interested in, they'll generally be homogeneous, or if they're non-homogeneous, we'll talk about how to use a homogeneous piece to generate solutions. Right, so what if our initial condition is some general function that's not necessarily given as this sum? Right, so then the question is, how do we go about, right, matching up these initial conditions. So maybe one way to recast the question is, well, right, maybe not if f is equal to kind of this thing exactly. Well, okay, that's our end goal. That's what we'd like to say. And so now the question we're going to ask is, well, in what situations does this equality hold true, right? In what situations can we write f as this linear combination of these sine functions? Okay. And so all of this stuff is getting into this notion of a Fourier series. And I have it written later, but the big idea is, how do we deal with these objects called Fourier series, which are built off of these trig functions. Okay, so Taylor series, you look at these infinite expansions in terms of polynomials. Fourier series, you look at these infinite expansions in terms of trig polynomials. So there are a few claims that we'll talk about later. Okay, so first one is any nice enough function, a smooth, piecewise smooth, continuous, piecewise continuous, whatever nice enough function you want. Claim as well, it can be well approximated by these sine functions. Okay. And so we may not actually get the exact function f, but we'll get pretty close with respect to some notion of distance. Second claim is, right, the approximation might not be good for just a few of these terms, right? Or maybe up here, if instead of taking this infinite sum, maybe if we just take, right, a finite sum, and this m is equal to 1, 2, 3, or something small, then this approximation may not be super good. But as we add more and more terms, then the approximation gets better and better. And so one way we might write this mathematically is, well, if we look at kind of how far apart this function is, we measure this distance between the function we care about and this finite series of sine terms. What we would like to say is that the difference between these two functions in some notion of distance, that difference goes to 0, right? So then this piece right here converges in a sense to this function. Okay, so we write 0 while we're taking a limit as we're adding more and more terms in this expansion. So the claim here is that approximation gets better as you add in more terms. And so then the third claim is, well, right, what if you take this limit? What if you were able to evaluate infinitely many terms? Then this function f is going to equal this infinite series. Again, for nice enough functions or most functions we care about, however you want to state it. Right, so then in practice, if we can express our initial condition as this sequence of sine terms, this linear combination of sine terms, then our solution, u, if we just take these terms here and then tack on this e to the minus k n pi over L squared t, which I've written right here, if we just tack that function on to each of these terms, then what we'll see is that, so this function here, which is given by this expression, solves this PDE, solves these boundary conditions, and then it also solves this initial condition, right? And you can double check by plugging in t equals 0. That's going to go to 1, and we're left with this. Okay. Okay, great. So we have a strategy, right? We want to take our initial condition, f, and we want to write it in terms of these sine functions. We want to write f as an expansion like this. And so now the question is, right, how do we actually compute these coefficients B sub n. Okay, so we have a systematic way of doing that. We like systematic ways, and we'll talk about that in the next video.